Hanging out.
Okay, so it's 3 o'clock, so I think we'll get started. So welcome everyone to the Winter 26 Stanford and Beverly Penner Distinguished Lecture. My name is Stefan Smith. I'm the chair of the Mechanical and Aerospace Engineering Department. I won't speak for very long. I'll hand this over to our faculty host who will introduce the speaker. We have this distinguished lecture series, a gift from the Sol Penner. It's wonderful to invite you all to listen to a distinguished guest, who today is Malcolm Smith, Professor Smith from the Cambridge University Engineering Department. He'll talk to us about, I won't spoil his title, but System State to the Racetrack. And I'm going to hand over to Professor Kristich, who will introduce him. Just one last thing. I am no Formula One expert, but I have driven past the Williams Formula One Center many times over the years. And maybe I'll find out more about what happens inside there this time around. So, Miroslav, over to you.
Thank you. Thank you, Stefan. So it's a great pleasure and honor to welcome Professor Malcolm Smith to the panel lecture here. It's a dream of every theorist that what they're doing for sheer pleasure, intellectually and even aesthetically, turns out to be spectacularly relevant and impactful. It's a set of measure zero that actually happens, but the existence proof is here with us. So let me be brief and say what is typical on these occasions. Professor Smith, in terms of his academic background, is the easiest to introduce. He is a Cambridge man all the way through, from his undergrad to his degrees in mathematics and engineering, to being a professor his entire career, almost his entire career there, to being the head of the control group there. He is not a stranger to this continent. He has spent a postdoc with arguably the most eminent figure in our field, Professor George Ames in Canada at McGill University. You were on the faculty at Ohio State?
Adjunct, yes, and postdoc.
Oh, okay. Yeah. He is one of the people who has made impact with his publications measured in many ways. He's the recipient of not one but two of the most prestigious paper awards, the Axel B Award of the Advocate Transactions on Automatic Control. He's famous for his work in robust control, network synthesis, nonlinear systems analysis, and what we're going to hear about today. Let me be very brief with Malcolm's honors and just highlight two additional big ones besides Axel B. He's last year's recipient of the Control Systems Awards of IEEE. This is the highest medal that IEEE gives for control, and he's a fellow of the Royal Academy of Engineering. I will let Malcolm say a word or not about his contact with San Diego and what San Diego represents in his relationship with America. I will not steal that opportunity from him. Let me just say the last thing. There's more to the man than control theory and Formula One. He's an incredible organist, and I had the pleasure 2 years ago to the famous conference, Mathematical Theory of Network Systems at Cambridge, which he organized, to hear him play in the Trinity College on the organ. And I don't remember the repertoire. Of course, there was plenty of it, but maybe something else. I do have it in my set of videos on my iPhone, but I'm not going to play it now. So with that, Malcolm, it's great to have you.
Miroslav, thank you very much. I just want to check that I'm audible. I'm coming through the speakers. All right, is that yes, good. Well, this is actually only my second time to visit San Diego, and I think Miroslav alluded to it. It was my first visit to America as a poor graduate student attending the ACC conference in 1984 to the hotel in Mission Bay. But I stayed at the YMCA in downtown San Diego. But I'm very honored that I'm being given luxurious accommodation this time for this second visit. And I think you're very blessed to live and work in San Diego. And it's a jewel, a wonderful place. I've had a chance to be shown around by two colleagues in recent days. I'd like to show this picture of Sol Penner, who I didn't know, but he's the reason why we're all here today and why I'm giving this lecture. I know he's a very, very important person for this university, who's the founding chair of the Aerospace and Mechanical Engineering Department, and he did so much to build up the university here. And so I have the privilege of giving the Stanford and Beverly Penner distinguished lecture today. So I'd like to start off with some motor racing history. This is Ayrton Senna winning the Monaco Grand Prix in 1987. And it's motor racing history because it's the first time an actively suspended racing car won a Grand Prix. It had been tried a number of occasions, but it was the first victory. And what is active suspension? Well, this is the Lotus, a schematic of the Lotus road car from around that time. And you can see accelerometers and gyros, hydraulic accumulators, valves, sensors, computers, and then at each wheel station, it looks like a McPherson strut, a spring with a damper, but it's not. It's explained in this diagram. We have a piston and cylinder, and with high pressure hydraulic fluid can be injected above and below the piston to extend and contract through this four-port valve. And you can see it's all controlled by the suspension computer, which is taking measurements from a load cell, a position sensor, and many other sensors on the car. So this is a control system. Fast forward 5 years, this is also a piece of motor racing history. It's the first time that the championship was won with an actively suspended car. This is the Williams driven by Nigel Mansell. And this is the beginning of the story for me. I arrived back in Cambridge. I spent 3 years teaching at Ohio State from 1987 to 1990. And I was appointed a lecturer in Cambridge immediately after that. The following summer, and I arrived as probably the most theoretical person in the control group with a background in robust control and so on. And through a chance phone call in the summer of 1991 from Paddy Lowe, who later became quite famous as an engineering designer and director in F1, I got involved in consulting on this very project. And it was tremendously exciting. So I was brought in as a control specialist, not knowing really very much about mechanical control systems or the particular needs in Formula 1. One of the main reasons and advantages of active suspension in F1 was due to the aerodynamics. The wings on a Formula 1 car produce downforce. And so that's in order that you can go around the corner quicker to increase the normal reaction. And of course, and the downforce is about 4 times the weight of the car at high speed. So you can drive an F1 car on the ceiling if you theoretically. Now the problem with a normal suspension system and even the tires as the downforce increases, the ride height reduces. And the aerodynamicists don't like that. They want to design a lift coefficient so they work at a particular ride height. So active suspension was very good that it could adjust for that, compensate, and be scheduled on the speed of the vehicle. So that's the first big advantage of active suspension for racing cars of this type. There's also other important aspects, ride and handling. Ride, how well the car responds to bumps in the road. That's how I like to think about it. Handling, how well the car responds to driver inputs like braking and corner. And it's a compromise. Here we are, an illustration. We've got the Cadillac Fleetwood sedan. And this is a wonderful ride. You're going along a bumpy road, you get a smooth ride, but coming to the stoplights or taking a corner, the body rolls around and it's uncomfortable for the passengers. The Ferrari Testarossa has great handling. So the body is well controlled under braking and under cornering and so on, but it's not very good on a rough road. So for the Ferrari, you need a smooth road, and for the Cadillac, you need a smooth driver. The Williams hardware layout was quite different than the Lotus, and you can see hydraulic links from front to rear of the car, for example. And the wheel station actuators were single acting rather than double acting. And there are a number of significant differences in how they operated. So this started to interest me. Active suspension is a great multivariable feedback control design problem. One brings the techniques one knows, but there's all sorts of extra things to learn and puzzling things for the theories. The different hardware layouts, hydraulics, passive elements, sometimes actuators and sensors are different. How to come to terms with this? We know how to derive control of it as control theorists when someone gives us the plant. But the plant, there's all kinds of possibilities there as well to think about. And then there are all these different performance specifications, ride handling, tire grip, and so on. And it's not a trivial control system for actuators and between 10 and 20 sensors. So the consulting and the applied work was very exciting, but I started to think theoretically, try to understand the fundamental trade-offs going on here. And so this is commonly done in the area to boil things down to the simplest possible model called the quarter-car vehicle model. So it's two masses and a force, an equal and opposite force that can be applied between the masses. And if it was a conventional passive suspension, that would be a spring and damper. If it's an active suspension, you're providing the force somehow. So this is a useful abstraction. And we've got road disturbances. Those are the obvious ones. And I found it useful to think about load disturbance as well, because in the F1 case, you've got downforce from the aerodynamics. So it's another pathway. And at least at a certain level of simplification, you can think of load disturbances as a surrogate for the handling input. It's a different transmission path. And so, for example, when you brake, you get induced loads on the sprung mass. Well, there's also induced loads on the unsprung mass, but as an approximation, you can think of, in a simple model, that Fs, as I say, is a surrogate for handling. The equation's 2 lots of Newton's second law, and what I'd highlight here, notice that the suspension force is minus u in the first equation and plus u in the second. And it was Carl Heidrich, the late Carl Heidrich from Berkeley, who made a very interesting observation. I bumped into this when I started working on this problem. If you take the sum of those two equations, u cancels out. So the control force doesn't have any effect on this particular equation, which you call the invariant equation. And there are certain consequences. So if you look at road disturbances, for example, you can look at a transmission path to various things, sprung mass or sprung mass acceleration. That's ride comfort is what that transmission path is used to evaluate. Tire deflection is sometimes thought of as a handling input, but it's also called mechanical grip, how well the car is staying in contact with the road. And to prevent too large a deflection there when you're going over a bumpy road surface is important. Suspension deflection, if you've got limited travel, you've got to worry about that. The important thing here is that these three transmission paths turn out to be dependent on each other. In other words, if you design one, the other two can be calculated from the invariant equation. So already that's an important insight for the designer, no matter what you do. If you design one pathway, the others are fixed. The handling one from the force on sprung mass there's a similar, the invariant equation applies there also, but it's a separate pathway. It's a different disturbance than the road inputs. So I started to work on this and looking at questions, as one does as a theorist. You take a problem like this and you try to develop insights. What is the complete freedom on a given transfer function? And the methods of robust control that we were familiar with at the time allowed you to get nice, necessary, and sufficient conditions on what was possible and what was not. And this is hardware independent. So again, I found that very useful, that you could have a benchmark before you decide on the layouts of actuators and sensors and whether there are passive elements. You would know what was possible. And so you could even ask, what is the minimum number of sensors to achieve a certain effect? Are there conservation laws? I'll show you one. And can the disturbance paths for ride and handling be adjusted independently? That's the invariant equation doesn't prevent the ride and handling being independently adjusted, of course, and that's one of the big attractions of active suspension, that you try to have a car that's like the Ferrari for handling, and it's like the Cadillac for ride. And that's the aim of such systems. I just show you one conservation law, which is very familiar for people who've taken advanced classical control courses. So what we're looking at here is the grip transfer function. So with the transfer function from undulations of the road surface to deflections of the tire. And what it's saying is the 0 dB line, that's modulus 1, no amplification. The green is when the deflection of the tire is less than the excitation of the road at a particular frequency. And the red is where things are worse. And the result, the area formula says that those two areas are equal. So no matter how clever you are, active suspension, whatever, there are going to be areas, frequency ranges, where the mechanical grip is worse, where there's actually amplification. So you need to bear that in mind in the design. So moving on just 2 years, Williams won the championship in '92 with Nigel Mansell, and with Prost in 1993. Active suspension was banned for the '94 season. Now, why was that? Well, technologies come and go all the time in Formula One, and sometimes there's no logical reason why things are banned. Active suspension was not on the radar at all for being banned when people were not getting it to work. It's only when one team gets ahead and the races become boring because the same team's winning all the time, that then the focus comes on the technology. And so it was. It was banned in the '93 season. There is something very sad happened in the '94 season in the Williams car. Ayrton Senna was tragically killed at Imola. And I give this quote here. I think it's the only time when active suspension was mentioned in a Times leader column. initially the cause of the crash was debated and was not properly known. And people pointed the finger at the ban of active suspension and said, well, the cars are now more difficult to drive because the aerodynamics has been tuned. It's so sensitive. Now with a passive ride, they're much more twitchy. Is that the reason? It turned out not to be the reason, but it was a fracture in the steering column that was the cause. But I just mentioned that, and I think now I'd like to move from that very sad event to come back to how I responded to this as a theorist. It's very wonderful to be working on these systems and doing theory at the same time, and suddenly we weren't allowed to race them anymore. So let's go back to the quarter car and compare. On the left, that's a conventional spring and damper suspension. On the right, we have an actuator and a controller, and we're making measurements on the system. And so the work I'd started to do in active suspension was very much focused on what are the limits, what's achievable, what's the maximum you can achieve with an ideal actuation system and a sensible set of sensors. So it was natural to say, well, can we do the same thing? Sorry, I keep pressing the wrong button here. I'll get used to it. What's the best we can do on the left-hand side using similar techniques? Okay, so I thought this would be a quick and easy theory paper. I knew some theory from my PhD time about passive impedances, electrical impedances. And so I thought that, well, conceptually, you can replace the spring and damper by a general passive black box mechanism. And if you don't have a power source, it is not active, that would be the most you can do. And then the natural thing is try to optimize over that class. And so can we characterize the properties of such a mechanism? Okay, so let's think about the electrical case. So we're thinking in black box terms, an electrical network, two wires coming out, a current I being drawn, and a voltage across the terminals. And the admittance is current over voltage at the driving point, the Laplace transforms of those, and the impedance is the inverse of that. Now, what was shown back in the 1930s is that a necessary condition for an impedance to be passive is that it must be positive real. So if you draw the frequency response of such a linear time invariant impedance function, it must always lie in the right half plane, can't enter that red forbidden region. And that it's necessary is not too difficult to prove, because the power drawn is its product of current and voltage. And what we're saying here is the phase shift is between minus 90 degrees and plus 90 degrees. So if you take current times voltage, Parseval's theorem, you get two sinusoids. They can be shifted by a maximum of 90 degrees. If you use simple trig formulae, you find, and you integrate over a whole cycle, you find that you get a positive number when the phase shift between those two sinusoids is less than or equal to 90 degrees. If it's more, then it becomes negative, and you can have a continuous cycle and pull power out on a continuous basis. Now, the really clever part is that the converse is true, that if you take any rational function that's positive real, that has an impedance function, as I've just described, then there's a circuit realization to implement that function. And that was first shown by Brun in the 1930s as a student at MIT, or a postdoc, early career. but he needed resistors, capacitors, inductors, and transformers. In 1949, there was a beautiful construction of Botton-Duffin, which showed that RLCs are enough. So the three basic two-terminal elements, resistors, capacitors, inductors, there is a circuit arrangement to realize any rational positive real function. Okay, so that's the theory that I knew from as a PhD student. And I thought, okay, well, what we do with a Formula One car, we optimize now over positive reals instead of the spring and damper. Okay, so the next stage is, well, how do you build? We know there's an electrical circuit. How do you build a mechanical one? So there is the old analogy, which is still the one that's taught mostly, connecting mechanical to electrical, is the force voltage analogy. Goes back to James Clerk Maxwell. So voltage maps onto force, current onto velocity. Notice that the product of voltage and current is a power. Product of force and velocity is a power. So it's that mapping is passivity preserving. So if we have an electrical circuit which is passive, we should be able to have a mechanical circuit which is passive. Electromotive force, it gives the clue to why voltage was mapped onto force. People thought that voltage was a bit like force. It was the thing that drove something and produces current in response. Around about 1930, three people, Darius, a Frenchman, Heinle, a German, and Firestone, an American, said, well, actually, it's better to do it the other way around, to map current onto force, voltage onto velocity, and then you get also electrical ground, the datum voltage, mapping onto mechanical ground, a fixed point in an inertial frame or a point with constant velocity. And an advantage is that this respects topology, that the terminals and nodes and branches map over exactly. So that was pointed out by all three. The mapping is underpinned by a notion of through and across variables, which was the proposal of Firestone. And his proposal is the more powerful one in my view. Floyd Firestone was a professor of physics at the University of Michigan. There are not many pictures I could find. This is one on his Wikipedia page, and he's been presented with an award at the American Acoustical Society of America. And so a through variable, he said, sort of a through variable is going to be force or current. It involves a single measurement point, and roughly speaking, your system needs to be severed to make the measurement. The across variable, so thinking of displacement, velocity, or voltage, you can measure it without breaking into the system with a probe. And the network analysis, this is the important point, needs the difference of the variable between 2 points in this case. So if I go schematically draw elements here, the electrical one, that's familiar. We've got the two terminals, the two nodes. We've got current coming in at one and current I coming out of the other, and V2, V1 are the two nodal voltages. The mechanical element is very natural now to write it. So we think of equal and opposite force. Well, the F is turned around in time, but that's not really, that's not a fundamental difference. And we're talking about velocity at one terminal minus velocity at another, or displacement at one terminal minus displacement at another. So you can see how they match up nicely under this force current analogy. And mechanical terminals, they're just attachment points. You know, a damper has two terminals, and those get attached to other things in your mechanical circuit or mechanical network. So it's nearly 100 years since the force current analogy was proposed, but people's notes still are very slow to be updated. So you find that the majority of courses around the world on system analogies still follow James Clerk Maxwell, the force voltage analogy. So the best book, the force current analogy, is this one, Shearer, Murphy, Richardson from 1967. And MIT really had a good go to change to the force current analogy in their teaching. I haven't checked whether they're still persisting with it. Cambridge had a go in the 70s, and somehow it got, when the lecturers changed, it got abandoned. It went back to the old system. We're having another go. But most courses still use the old force voltage analogy, which I think is a pity. Another thing about Firestone, what about the mass element? Let's think about that from a terminal point of view. So Newton's second law, we're looking at the motion, the acceleration of the center of mass relative to a fixed point in the inertial frame. And so Firestone said, actually, the mass is analogous to a grounded capacitor. And he proposed this symbol. So it looks a little bit like a slide or something moving in and out. But for point mass, there aren't two terminals. There aren't two terminals that are freely movable in space. There's just one terminal. So in Shearer, Murphy, Richardson, in Firestone, you find then this mapping. The spring is now mapping onto the inductor. It's not the one we taught in school very often. It's the other way around. But this is the force current analogy. Whoops. Which way? There we go. Damper and resistor, of course, those map over in either analogy. And then we've got the mass analogous to a capacitor, but it's highlighted there in red because it's only got one freely movable terminal. All right, so at this point, there's nothing new here. There's nothing I'm describing that wasn't well known. But at this point, I'm a little annoyed because there's a snag here that's holding up the theory paper. And what to do about this? So the synthesis theory doesn't work with the mass element. First of all, if you've got an electrical circuit with ungrounded capacitors, you won't have a direct mechanical analog. And you can very easily find circuits within the class where you need ungrounded capacitors. So you've got a problem there. And the mass element also, if you have a 3-ton mass that you needed inside your circuit, that wouldn't be very good in the suspension system. So the black box impedance you want to connect between the unsprung mass and the sprung mass should have small mass. So that's the second advantage. So floating around in my mind was this question: is it possible to construct a physical device so that the relative acceleration between its endpoints is proportional to the applied force? So we're looking for a device with two terminals, which are freely movable in space, and which will have the property that the equal and opposite force at the terminals is proportional to the relative acceleration between them. I wasn't thinking that the answer would be in the positive. I was thinking of ways to prove that, well, what we all read in the books is the way it must be, and that you're stuck with a spring and damper. Okay, it shows that you sometimes should think positively, and thinking positively led quickly to this idea that if you take a housing and a plunger sliding in and out, and a rack and pinion, and a system of gears attached to a flywheel, if you move this in and out, actually that is a good approximation to what we're looking for. something where force is proportional to relative acceleration. Okay. So that was my first thought, and I thought one should be careful about inventing new words, but after some reflection, I thought it was justified to highlight the concept, to invent something. So that this is the word I chose, inerter. And the ideal inerter is, okay, ideal modeling element. All the others, we have ideal modeling elements, which are have the mathematically perfect linear law, and that's different than the physical realization doctrine, which approximates the law. So here's the ideal inerter. It's a mechanical one-port device such that the equal and opposite force between the nodes is proportional to the relative acceleration between them. So it looks a bit like Newton's second law. Force is a constant, which I think it's natural to call inertance. Its units are kilograms, and that v2 dot minus v1 dot, that's the relative acceleration between them. And its units, its units are kilograms, and the construction I just showed would allow you to have a large number of kilograms for a device of small mass, which is a key thing. And the stored energy is a familiar formula, half b times the relative velocity squared. And I think that construction shows that it can be approximated. The ideal inerter can be approximated in the same way that real springs, dampers, and inductors can be approximated. And we can assume its mass is small. So you can think of other ways of realizing them. You can have a rod with a screw thread and, for example, a ball screw and a nut, which spins the flywheel actually about the rod. So here's the first one we made in 2003 in the engineering department at Cambridge with a mass of about 1 kilogram, and the inertance is about 150 kilograms. And if I slowly dismantle it, remove the housing, you can see the screw thread, you can see the flywheel there. Now the flywheel is removed, but you can imagine here holding the end piece in your right hand and the housing with the white pegs in your left hand, moving this in and out, then the nut in the center spins in proportion to the position. That's a close-up of the thrust bearing. Now, British Airways were kind enough to allow me to bring one in my baggage, and so here, this is the one. Yes, as I say, it's been passed around in lectures many times, so it seems to be surviving. The thing to do, I'll pass it round now. The thing to do is try to get it to the middle of its travel, and then move it just a little bit in and out in a sinusoidal motion. And remember, the inerter is 180 degrees out of phase with the spring. So when you get to the maximum extension, the force is pulling rather than pushing. The spring will push you back. The inerter pulls you in the opposite direction. So yes. So the synthesis then, so that's the element that I like to draw for the inerter, with it representing the flywheel capacitor with the ends filled in. And so that's for network synthesis. The mass doesn't go away. The mass is fundamental. You still have the mass everywhere. But for constructing positive real passive impedances, then we can use this for synthesis. And so I just to finish the point, I like to write down as a theorem it's possible to build a passive mechanism of small mass whose impedance force velocity relationship is any positive real function. And we're using the Bott-Duffin theorem, we're using the force current analogy and the ideal inerter to establish that result. Just to run things home, I'll be an evangelist for the force current analogy. I'd like to show you on the board. I'd like to do the force current, do the electrical analog of this of the quarter car. So I'm going to have electrical ground here. And the unsprung mass mu. That's a capacitor which is grounded, and then the sprung mass is another capacitor which is grounded, and the suspension system, well, it's a spring and damper, so resistor and inductor. This is wireless. That connects between those two terminals. The tire now, well, the constant becomes inverse, KT inverse. Now, this here is ZR. So what about the road? Well, actually, you can think here, ZR dot of a velocity source. That's a road excitation, and on this side, so that's a voltage source from the velocity source, and we here have Fs, which is a current source. Okay, so that's the circuit. I'll bring it up here as well. That's the equivalent electrical circuit with the force current analogy. You see how easy it is. And I especially like to draw this picture because it allows my favorite joke to the vehicle dynamicists to remember that the sprung mass and the unsprung mass are connected to ground, but the tire isn't. The tire's connected to the road. So at this point, the calculations showed that adding the inerter to the suspension, you could achieve improvements that you couldn't get with a spring and damper. So here on the left, the red curve is the best you can do. They're very stiffly sprung, so that they oscillate a lot. And this is the least damping you can get with springs and dampers only. And the dashed curve, you can achieve that with inerter. So surprisingly, the inerter is an energy storage element, not a dissipator, but it allows you to reduce oscillation in combination with the dampers. And you can see the impedance function, the phase goes positive, so you're getting phase advance, which you can only achieve with inerters in the suspension. At this point, Adrian Newey and Paddy Lowe had moved to McLaren, and so it was natural for me to approach McLaren with the idea. They signed an agreement with the university and developed it, and this was the first race with Raikkonen. He got McLaren's first victory of the year with the inerter, and well, we had a very strict confidentiality agreement, and so for 2 years, people were asking me at Cambridge, "How are you getting on with that inerter stuff? Weren't McLaren interested?" Meanwhile, they were really winning races, but I couldn't tell anyone. And McLaren, they invented their own name for the inerter, the J damper, and the idea was to prevent links to other teams, prevent if people left to go to other teams, they wouldn't connect it with the technical literature. And the J damper came into the public domain in 2007 because there was something called the Espionage controversy, and Ferrari were found, McLaren, there was a McLaren employee, Mike Cochran, who had a buddy at Ferrari, Nigel Stepney, and who gave Cochrane a floppy disk with all the current Ferrari drawings. And Cochrane's wife went down to the Xeroxing shop in Woking and printed out 700 pages of Ferrari top secret drawings. And it just happens that the lady in the shop is a Ferrari supporter and ready to run. So McLaren got into a bit of trouble for this, even though it wasn't clear that the drawings had much effect on their, if any, on their program. And they were taken to the FIA, and there was a World Council hearing. McLaren were found guilty, and they were given the largest fine in motor racing history. And it's the largest fine in sporting history still. They were fined $100 million. After that, McLaren said, well, hang on, there's quite a lot of this going on because people leave and go to the team and take ideas. We know somebody went to Renault and took some of our ideas because we hired someone from Renault back to McLaren and they told us about it. So on one of the drawings that was taken was a drawing of the inerter of the J damper. And so Renault was taken to the World Council and they were found guilty. And their fine, for anybody knows, it was zero. No, there's not enough time to explain why there's such a large discrepancy, but it's partly the personalities involved in the sport. But the reasoning that the FIA gave that Renault were not fined, let me see, was, this is the extract from the decision. It turns out that Renault tried to get the J damper banned under an erroneous interpretation that it was a mass damper, because they developed the mass damper and it had been banned. They said this is the same, it's the mass damper. And so the World Council said the fact that Renault fundamentally misunderstood the operation of the system suggests that the J damper drawing did not reveal enough to Renault about the system for the championship to have been effective. So guilty but no fine. This was a sweet moment, I think, when this picture came to light in 2008, because this is the tri-links, the front tri-links on the F1 car. And this was the spot that was pioneered by McLaren for the inerter. And you can see here, there's a housing and a rod here with a screw thread. No one ever had damper rods with screw threads before this point. So I think this is the red team being caught red-handed. I wanted to, I skipped over it. This was the mass damper idea that Renault had. So it's a mass on a spring based on the springs. And that's fundamentally different than the inerter in parallel with the spring and damper on the right. Yeah. So after the story broke, Penske in Reading, Pennsylvania, signed an agreement to be one of the suppliers of inerters in Formula One and in other areas of motorsport, and they're still continuing to supply devices. Other possible applications, wherever you're looking at vibration absorption, then it comes into question. You can replace springs and dampers, you can add the inerter in. So the buildings, it's gone the furthest in terms of actual application. Trains, we're still working on this. Motorcycles, there's an advantage in terms of control for steering. in terms of control of weave and wobble instabilities. And helicopters, you can build mechanical notch filters to suppress a particular frequency with inerters. And so a potential application in helicopters. The inerter, once you get outside of the Formula One world, the inerter will compete with other technologies, active and semi-active technologies. So the cost of making an inerter has to be balanced against an active system. And so it needs to find its niche in a particular application in terms of packaging and cost. You can also make them with fluids. Here's one idea of having a helical channel. And so as you move, you've got a double acting piston here, you're pushing fluid through a long channel. So the ratio of areas between the piston and the helix is the gearing ratio, and the mass of fluid in the helical channel is the mass. So that's, you can see it's trying to be like an inerter if you have enough mass in there. Of course, you've got viscosity, so you're going to have damping effects. And you get, we've studied this, you get interesting non-linear damping characteristics with such devices, in addition to the inertance effect. To finish off, I think I just want to give you a snapshot of some research spin-offs of the inerter idea. Circuit synthesis was a very active field until about the late 1950s. Then active circuits came along, and people left the field. But there are certain questions. For example, the Bott-Duffin construction is possibly quite wasteful in terms of number of elements. So we had a look at what were the most efficient realizations, and that's relevant in the mechanical domain. I call that the top-down approach. You start with a positive real, and you find the best realization of a particular function. The bottom-up method, the classification method, is asking, you study families of networks and you look at their realization power. So you carefully understand simple networks and what are the best combinations. So another interesting direction, I was involved in collaboration with McLaren Automotive. For this particular car, McLaren 720S. So this is a semi-active. So we had a project with them together with Will Holt and Panos Presas. So the hardware, when we came into the project, the hardware was already determined. There's interconnected hydraulics, but there are adjustable dampers. So I think this picture is the best view. So it's a regular damper with an orifice, but you have a needle valve which adjusts the size of the orifice, and you have a solenoid that can jiggle around the needle valve at a high rate, and so you can adjust the damping rate. And so we did. It's a non-linear problem, but then you've got to figure out road inputs and driver inputs, how best to design this feedback. So the one thing that would be another story to explain that system. I'd just like to talk about a follow-on that we did with colleagues at UC Irvine, Trifon Georgiou and Faryar Jabari. Variable resistors, they're standard. V of T is R of T times I of T. Adjustable dampers are exactly analogous. And so the question is, what about variable stiffness springs? People talk about variable stiffness actuators, but you can quickly show, I just sort of flash that calculation up. You can show that that's actually, you're right, F of T is K of T, X of T, and you're allowed to adjust the K. you can show that's an active device. That has to be an active device because you can cycle it. You can find a trajectory getting back to where you start with, where the net energy over that cycle is positive. So you can pull the power out. So the question is, can you make a losslessly adjustable spring? In other words, so you could have a little dial on the spring, you could adjust the stiffness in a lossless way. Well, we've puzzled about this a long time, and in fact, we have a construction. I won't have time to show you today, but the law is very interesting. That here's a spring. It doesn't look like a law for a spring, but you've got x dot velocity is p, which is something that's variable, times d by dt of pf. So you've got p inside and out. Now, if p was constant, p would pull out of the d by dt, you'd have p squared. You'd have x dot is p squared f dot. So displacement is proportional to force. So that would be a spring. So it turns out that that is Hooke's law in disguise. And there's an internal stored energy. You multiply both sides by f and integrate up. You have a stored energy. And so this quantity p is the square root of the compliance. The inerter, it works in a dual way. Force equals r d by dt r x dot. But r was constant, r would pull out, and you'd have f is r squared times the acceleration. I think I take 1 minute, I think, for the last thing. That's the final layout of the control system on the McLaren 720S. The observer here needed to think about exogenous inputs as well as estimate the input as well as the state. And so we've started on a direction for estimation, which is a generalization of Kalman filtering, where you throw the process noise away. You have the measurement noise, but no process noise, and you estimate the state and the input on an equal footing. So this is joint work with Greg Gartus. And I just flashed this up to say you can get Kalman filter recursions. It's a generalization of the Kalman filter, but it has state update, input update, and propagation. I'm not going to go through that. Final slide is there's an interesting application of this that if you go back to the quarter car, you can think of, well, how do we measure what do we want to try to measure the road profile? So that's an exogenous input, which you could say is completely unknown. You can instrument the car with an accelerometers on the two masses, strut deflection and GPS, and it's an inversion problem. You can find with this filter the road profile without profilometers. I have perhaps run over time slightly. There's a lot of people along the way that I have to thank who participated in this work. And once again, it's a great honor to give this panel lecture.
Questions, please.
Yeah, a little bit.
Yeah.
So the example you mentioned of the mass damper system, you see there's a lot of buildings, to
Yes.
dampen a particular resonance modes.
Correct.
So it's like they use that impedance impedance matching. They use that as a terminology.
Yes.
Can you flesh it out? Can you maybe shortly explain to me or to us, I guess, why they're fundamentally different?
Yes. So
By the way, if it takes too much time, we can take it offline.
yes. Yes. So if I can go back to that particular diagram, you see the mass on a spring produces a force only on the sprung mass. The inerter here produces a force on both, which is equal and opposite. So the dynamics of the two are different. Yeah.
Oh,
So-
so as a result, the frequency response will be different?
Yes.
Oh, yeah, okay. I see.
Yes, yes.
Okay.
There's also, there's an advantage here. With the conventional vibration absorber, you're adding mass to the structure. And one limiting factor is how much mass you're prepared to add on. You might want to double it, but that's not practical. It's increasing the overall mass. Whereas there's no limitation here with the inerter. You can have 1,000 kilograms, 10,000, 100,000 in a device which,
Nothing. Yeah.
yes.
Thank you.
I do have a question.
Yes.
So I remember when you gave me a tour of certain parts of Cambridge that are registered that your favorite Cambridge guy is not Maxwell, but Ralph. So here is that, you know, you're now even choosing an American over Maxwell. But now here's a question, a serious question that is related to that.
Yes.
So these are all linear elements, ideally.
Yes.
But in the inerter, you have rotation, whether it's the pinions or the flywheel, you achieve this with rotation. So then I'm thinking about the electrical equivalent. There's no solenoid without a rotating field, without electron rotation. So there is an analogy there that fascinates me. I have not understood it fully, but what I see is that if we accept that analogy, then it appears that Maxwell would be right. That analogy would be right because in his framework, it is the solenoid that is the equivalent to the inerter rather than the capacitor.
Yes, as soon as you have a stored energy, well, I recommend Firestone's paper because he argues it all through. We've been taught in school that inductance, the stored energy is like mass. And here's the argument. He said you can argue it just the same way with two plates and a charge. And why do we prefer one? They're both analogies, aren't they? They're not the same microscopically in that we've followed the trace all the way up to the macroscopic devices. They're analogies, they're not exactly. See the sort of limits on travel that you have with a mechanical device. And that's a significant issue you have to think about. But that's displacement. So that would be, in the force current analogy, that would be the integral of voltage. Some people call that flux linkage. Coming from inductors, but you can have integral of voltage for a two-term element, which is not an inductor. So flux linkage is a misleading term there in a certain sense. So I'm sorry, I'm going around in circles, not answering your question. I think my basic point is that I don't think you can go down to fundamentals, to microscopics, and say that magnetic fields are analogous to what's going on mechanically. It's the lumped elements. It's been observed for more than a century that they obey similar laws, and we like to map between the two. And the fluid systems, of course, you have through and cross variables there too. Pressure would be on a cross variable, P2 minus P1, and flow rate would be a through variable. So,
Can you
yes.
also explain how could you get a high inertance without a high mass? For example, a flywheel is simply by putting a certain mass far away from the axis of rotation.
Yes.
You get
So the little Meccano model, which I didn't bring with me, has two 5-to-1 ear trains, And the radius of gyration ratio to the pinion radius for the rack pinion is 2 to 1. So it has a multiplier of 50. And that squares up. And the mass of the flywheel in that example is 100 grams, 0.1 of a kilogram, times 2,500 gives a mass of, gives an inertance of 250 kilograms. So this little McLaren model had an inertance of 1/4 of a ton. Now, if I had put in another 5 to 1 gear train, which is quite easy, that's another factor of 5, which squares up is 25. So then I would have had 25 times 1/4 of a ton, which is how many? 6 tons or whatever. So there's, by gearing up, we've made it's easy to make high inertance device without increasing the mass very much. They eventually become very, very stiff.
Are there formulas for equivalent inertances of series and parallel connections?
Oh yes, oh yes,
What-
that's what
what
I said.
Yeah.
It's all, yes. So if you put 2 inerters in parallel, then you sum the inertance. If they're in series, then it's half. Yeah, they're the same. Yeah. So to say exactly all the same formula, because it's completely it's not even an analog. It's just a straight mapping which is topologically consistent between mechanical and electrical circuits.
Other questions? Yes.
I would like to first thank you for a very nice, concise presentation. I particularly like the logic flow. You start from the question, the existing state, and you come very logically to where you are now. It's also a good example for all the students to question, to think outside the box. Even though the things were around, say, for dozens or hundreds of years, doesn't mean it's always correct.
Yeah.
That is just a statement. The question is, I understand the inerter has been now banned from F1
Correct.
racing. Unfortunately, I think it's unfortunate that the dynamic absorber was also banned or active.
Yes.
And so on. That's a separate. But now that it is banned, maybe you can tell us what is the actual structure that you had in F1? Was it simply parallel with inerter or was more complex?
It's a very good question. People only ever implemented an inerter in parallel with a spring and damper in F1. Even though the theory shows that it would be better to have a spring in parallel with a series connection of an inerter and a damper. And that's entirely realizable. The reason why it wasn't done is that the grounds under which the mass damper was banned, that movable mass was considered to be a movable aerodynamic device, something that can move independently on the car, which can affect the aerodynamics. That's how they. I'm not justifying it. That's how they reason to ban the mass damper. Now, if you put an inerter in series with a damper, there's a node between them, which can move independently. And the people in the sport felt that as soon as they did that, that arrangement would be banned, and perhaps the inerter would be banned. We're a victim, but we were a beneficiary of the rule change in the discovery of the inerter, but we're also a victim of it in terms of what one might like to do in engineering terms.
I also want to thank you for a wonderful talk, and since it's now banned, how did you choose the value in kilograms of the inerter that was used by McLaren relative, for example, to the mass of the tire wheel system? Was that how you did it, basically?
Yes, well, we start off with simple models and starting off with damping ratio, first of all, but then with more advanced measures of mechanical grip. And you can optimize those, even if you can't solve a general analytic formula, you can find the minimum, draw a graph with performance measure versus inertance in kilograms, and then you look where the minimum is. So that's how it was done. So from simple models to complicated simulation models, and then you build an inerter with that, put it on the car, tune it a bit and see whether you get the effect.
And how many kilograms was it approximately?
How many kilograms? So they started off around 50, 80 kilograms, and then it gradually increased from there. So in the series arrangement, you find that, sorry, in the parallel arrangement, the mass, the inertances are smaller and are comparable or a bit smaller than the sprung and the unsprung mass typically. But of the same order of magnitude of the unsprung and sprung mass. That's how it turns out when you do the calculations. In the series arrangement, then it might be 5 times higher.
So similar to the mass of the wheel tire,
Yes,
it ended up approximately.
yes.
Yeah.
Yeah. For the parallel arrangement, it's higher for the series, but that was never implemented.
Thank you.
No.
All right. Well, thank you.